Please, Daniela Sayo, please. Okay, she already started recording. Okay, good morning, students. Today is June 23rd. We're going to start chapter 3 today, okay? Yesterday, I sent you a link so you could see a very introductory video on this topic, okay? Usually when you talk about Newton's law in general, right, you can see a body and you see forces on the body, right? And you can imagine equilibrium, static equilibrium, because you see forces downwards, so we are expecting to see forces upward in order to equilibrate. Also, in the torsion or torque or moments, right? You see something like that, and you recognize that there is a net moment like this. So there must be another moment, another torque in the opposite direction, right? In order to equilibrate. That's physically, you can see that. For example, in the evaluation, the quiz, you have 3 forces pointing downward, and you had the buoyancy distributed on the whole acting in the upward direction. So you like it's like physically imagine or foreseeing the equilibrium of static equilibrium of the system. In this chapter, we're going to use energy in order to calculate the deflection of an structure, for example. And it's we're going to lose this physical perspective, okay? Because we are going to work with a scalar, work, energy, and the direction, I mean, there is no direction anymore because it's a scalar. So, but in general, energy methods are extremely powerful, okay? And we're going to use some of this material in the next course on finite elements, and you will see that, okay? So when we work with in a single element, right, and you have some forces, okay, in the next class, we're going to take those forces and convert it into equivalent forces applied on the joints, right? And we do that using potential energy. So also, it's quite easy to analyze a little plate element, okay? If we use equilibrium, that will, it's in some cases, it's just impossible. But using finite elements and applying some of these energy methods, we can do it in order to deduce the stiffness matrix of these elements, plate elements, okay? So there is a lot of applications, but we lose this, it's like physical, how can I say, we don't see the equilibrium because there are no components of forces anymore. We will talk about energy. Okay, so that's the general idea, okay, what we are going to do. Of course, this is just an introductory chapter. We will complement this in the next semester with in the course on finite elements. Okay, so let me ask something. How many of you, please raise your hand, okay? I want you to raise your hand, those who had the time to review the video that I sent you yesterday. I posted in the Aula Virtual, in the module. Did anybody have the time? Please raise your hand, those who had the time to review that. Okay, please raise your hand, those of you who were able to see that. Okay. Okay. So this we have 6. Okay, let's go on. Miss Flores, Do you remember any concept, any topic in the video that you had to review?
Good morning, doctor. Yes, at the beginning in the video, this present a concept that we will be have external work that will be equal to a change in internal energy.
Okay, that's conservation of energy. Yes,
Yeah.
and that's one way that we can apply this energy principle in order to analyze the deflection of an structure. Yes, yeah, exactly that. Okay, it's extremely easy, but as you can imagine, if it's an easy way to apply, it can be applied only for very simple cases. We're going to do that today. Okay, yes, it's very interesting, right? Because when you talk about work or energy, you immediately think of an engine, right? Gasoline or something like that. So you relate that to energy. And in this case, it's a little bit different. As you explained it, yes, you apply a force, and this force, because of the deformation of the body, travels, is displaced. And once this force is displaced, it generates energy. And where this energy go? As you said, this is stored inside the body. Since you don't want this energy to disappear, you have these two terms, they have to be equal. And from there, we can go on and deduce an expression for the deflection. Okay, that's one way that we're going to do it. Okay, so good. Anybody else, any other person who saw the video and want to add something? Anybody else that want to add something? Anybody? Mr. Dominguez, do you remember anything else from video from yesterday?
Yes, doctor, good morning. The work produces force and displacement.
Yeah, that's a concept, right? Work is equal to the force times the displacement. That's energy. This energy has to go somewhere, right? And it goes into the body. Okay, good. Let's go on now. Let's see, class notes. Here it is. Daniela, can you see my screen? Full
Yes.
screen?
Full screen, no. No, yet.
Now?
Yes.
Okay.
Yes.
Okay, so this is chapter 3, as I said before, and today is June 23rd. So let me write that down so we can identify. So today is June 3rd. Okay. So these are the topics that we're going to be using, okay? So it's elastic strain energy, okay? So we're going to deduce an expression to evaluate this, okay? And as we said before, the work, which is developed by these forces, okay? This is going to be converted into strain energy. So we need an expression to evaluate that. And then we're going to use that to calculate the deflection using conservation of energy. So the work developed by these external forces has to be equal to the strain energy. And using such a simple principle, we can get some answers, right? The other principle that we're going to present and use is the principle of minimal potential energy, okay? And this principle, it's very it's widely used. And one of the ways it used is we're going to use in a very simple way here, okay? to analyze approximately the bending of beams. And then we're going to use that chapter 3.2 to calculate the critical load, okay, in buckling. So we're going to review that. This is something that you analyzed in solid mechanics, okay? You deduce an expression for this critical load. And we're going to do that, but using potential energy theory, okay? So more or less, that's the topics for this chapter. Okay, so these are the three terms. I didn't want to write anything here. Work, as somebody said, is the product of force, okay, times the distance displaced, okay? It's that strain energy, okay? That's energy which is stored inside a deformed body, okay? And also elastic limit. Anybody remembers what's the concept of elastic limit? People from solid mechanics, do you remember? What is the elastic limit? Anybody? Or you want me to call somebody?
Is the point of when the material can recuperate his elongation.
Yeah, its original position, yes. So we are going to be working below the elastic limit, okay? So since we are in the elastic area, we can apply Hooke's law directly, okay? So yeah, as you said before, it's like maybe we should put it graphically, right? We say sigma, epsilon, we have something like this, we have some yielding, and then we go up like this. So this is the elastic limit, okay? So we're going to be working in this area, okay? So this is the elastic area, elastic region, okay? So you can see that there is some proportionality between sigma and epsilon in general, okay? So Hooke's law, it's applicable in this area. Okay, let's go on. So these are the basic terminology that we're going to be needing during this class. The rest, well, you remember. Okay, so as I said before, okay, we are going to be using this concept. Now, energy, remember, it's a scalar, okay? So we have to be careful with that because there is no direction anymore. Scalar, okay? So we're gonna have one term, no components in X, Y, or Z, one term. Now, this is something that we're going to be using, okay? If we have a body, okay, like this one here, and you have some points of support, like this one here, and we apply a force, okay? Because there's some elastic, or there are some elasticity in the body, then it will deform, right? So let's draw a deformed profile of this body, okay? So let's suppose that we have something like this. Here it's like this. So this is the deformed file. Now, what's the point? The point is that here we see that there is some distance which has been this force, this is delta, that the force has displaced. Okay? So this is the force. And delta is the distance that this force has displaced. Okay, so as we said here, okay, this force multiplied by the distance is work. Okay, and this work, which is energy, right, has to go somewhere. And that energy, we will see that in a minute, basically it's going to be converted into elastic strain energy. I say elastic because, okay, we are, as we said before, we are going to be working in the elastic regime. Okay, that means that after, as Mr. Paredes said, after you take the force, the external force away from the system, you will return to the original profile. Okay, so that's a general idea of some of the applications. Okay, so this work developed by the external forces. They displaced with the deformation, the body is converted strain energy. That's the general principle that we're going to be using. Okay, well, that's one. We're going to use another one. I think we don't need this S here. There's an error here. This S here shouldn't be here because this is plural. Okay, that's the general idea. So what we need to do is to be able to evaluate two terms, work and strain energy. So let's start by evaluating strain energy. Okay, so that's why we go here. Now, you see immediately that we are saying that this is elastic strain energy. That means that we are going to be, it's a reminder that we're going to be inside the elastic regime. So we are not going to go beyond the elastic limit. Okay, so Hooke's law, it's available to us. Okay, so let's do this in several cases, and then we're going to put the whole thing together. Okay, so this is one single case in which we have normal strain only. Draw something like this. Okay, let's suppose that we have a small element like this one here. Okay, and let's suppose this is the X direction. Okay, so this is the original situation of the body. Now, after we apply forces, okay, this element, we consider only the deformation, okay, in the X direction. Okay, since we are only working with normal strain, this is, you can see here in the title, okay? So there's going to be only elongation in the X direction. That's the only deformation that we are going to consider for this case. That means that this will be transformed into something like this, okay? So it's elongates. So we are going to assume that the elongation is positive. There. Okay, so this side here is this one here, moves a certain amount U. And this moves the same as this one here, but a little bit more. And that's U plus a change, okay? Since we're moving from here to here, that's the only change is in the X direction. That means that this is equal to du dx times dx. Okay, So this is the difference between what this right face has moved with respect to the left one, right? Because both moves an amount U, but the right-hand side moves a little bit more. Okay, so this is the elongation, or the distance traveled. I'm sorry, here I should put the relative. Okay, so that's the elongation. So that's the distance traveled. Let me go back. Here we said that we need the distance, right? So this is the distance we were looking for. So it's du dx times dx. But now let's see at the force. Okay, now here, since this is in equilibrium, we have the force pointing to the right, and that's equal to sigma x times dA. And here, sigma x times dA. So that's the idea. And so that means that this force at the end of the process, sigma x dA has traveled this amount. Okay, so this is the force at the end, the application. Yesterday, I asked you to review this video. And do you remember the way they call this little piece of force? Anybody remembers how in the video that I asked you to see? Do you remember how they call this little piece of force? Do you remember? No? No, it was called little f, right? So you apply a little f and deform. Then you apply another little f and deform something else, right? And you were increasing the force, and because of this increment, you were continuing with this the increment of the displacement. So this is the final situation, right? So since you go increasing this force in steps, very little steps, then the work that this force has developed after you reach the final value is like an average of this final force. Okay, so it's like doing something like this. Let me here. So it's like, let's suppose this is the final force and this is the deflection. So when you go like this, okay, you apply a little force, then a little force, then a little force, okay, and here this is F, this is little f, and this is little delta. And at the end, you have this force, F, large F, and you have the final deflection. So the final displacement is du dx times dx. Okay, and the force is simply sigma x dA. Okay, but you can see immediately that the area here, this is the work developed by the force, the load, from the beginning till its full value. Okay, we have to be careful, because if we consider the full force from the first, that means that we're going to have a dynamic phenomena, and we are in the static range. So we have to start by applying a little force and a little force, and we go slowly increasing the value until finally we have the full F value on the body. okay? So that means that the work developed by this force and this energy is stored, okay, as internal energy. So work internal work developed by sigma x dA is stored as internal energy with value. This is what we were looking for. So we can call it du. So that's the internal energy which is stored in this little element, okay? That's going to be equal to what? 1/2, okay? 1/2 because we go increasing slowly, okay, the force until we finally reach the total value, and we simply have to multiply the stress, I'm sorry, the stress multiplied that by the area, okay? That's sigma x dAs, that's the final force, and by the displacement, which is epsilon x dx, okay? Here, we have du dx, and du dx is equal to epsilon x. Okay, so we can say here that this is equal to 1/2. We have dA and dx. That's the differential of the volume. So it's going to be equal to sigma x epsilon x dV. So that's the work which is developed by this internal force on this little element from the beginning of the process until you find the final value of the external force. So you start increasing, and finally you reach this situation. So this force on the ends moves how much? Dx epsilon x. That's the final displacement. But from the you start from zero, you start moving a little bit more. Okay, so you go slowly, and that's why we have to include this 1/2. Okay, but please, this is the case when we have one single element of the strain. That's in the normal x direction. That's why we consider only the displacement in the x direction. So there is no distortion, okay? So you have a rectangular original element, and at the end you have another rectangular element with increased length. There is no distortion. Now we are going to consider what happens if we have shear. That comes next, okay? Now here, in this little graph, okay, we can see that below this, we have the, what we call the strain energy. And above, okay, if instead of F and U, you consider sigma and epsilon, above, you have the, what we call complementary energy, okay? Now, since we are in the linear or in the elastic regime, the two triangles, upper and lower, have the same area, okay? So the complementary energy is equal to the strain energy when we have a linear process, okay? We can take this above the elastic limit, and in that case, the complementary energy will not be equal to the strain energy. But that's something that we are not interested right now. That's a little bit more complex. Let's deduce something similar, but for the case of the shear, okay? Let's use now in the shear case. And then what we are going to do is simply put the two things together, okay? So let's do this. So this is the case, okay? Similar situation, but in this case, we have only one element of the stress, and that's the shear in the XY plane. Okay, so On this phase, this is the positive X phase, the tau is subindexes are X, Y, okay? And up here is going to be the same, but the indexes, they change. Now, here, okay, this is a transfer view. Okay, so from here to here, this is the X, and from here to here, this is the Y. Now, if you will multiply this, okay, this is the area. So you multiply this by dy dz, right? You are going to move this distance. So you see that this distance is in the vertical direction. So this distance can be obtained using this angle. And this angle is equal to dv dx. Okay, so that means that you are moving in this direction. Okay, so this distance here is equal to this angle multiplied by the distance from here to here. So this thing here is equal to, this is a displacement, people. We have to be careful with the units. So this is equal to the angle dv dx, this dimension, which is equal to dx. There. Similarly, we have this distance. So this force here, which is acting on this face, okay, will move this this distance in the x direction here. So this is going to be similarly equal to this angle here, and that angle is du dy multiplied by the this radius, which is equal to dy. So this is equal to du dy times dy. Now, those are distances. Now we have to consider forces. Okay, so this force here, the vertical here, so this is the force in the y direction. So that's going to be equal to tau xy, and the area is going to be dy dz. And here, this force is pointing in the x direction, and that's going to be equal to the stress, which is equal to yx, and the area, you see, is equal to this is dz, times that, which is the x, so times the x dz. So we have a horizontal force, which moves du dy times dy, and a vertical force, which is equal to this value, okay, but moves a different distance. So this force moves this distance. This force moves this distance. So what we have to do is, since we have both effects simultaneously, we have to combine force and distance, and then we have to add. But again, since we are increasing slowly the application of the force until we reach these values of the stress, we have to consider the average. Okay, so let's do that. So the work, the internal work, which is developed by tau xy and tau yx, and which is stored internally as strain energy. is. So it's du. Now we have to be careful because let's put a little s because this is for shear, okay? So it's going to be 1/2. So we have this force in the x direction, so it's going to be tau by x dx dz, and then the distance is this that travels is du dy times dy. And then we have to add the other term. So the force is this one here. Tau is going to be tau xy. The area is dy dz. And the distance is this one here. So it's going to be dv dx times dx. So that's force displays a distance, force displays a distance. You add these two things and that's work. That work, that's energy, has to be stored internally. And that's what we are calculating. Okay, so we can say that in case of shear, pure shear, okay, remember in the previous case, we have only one normal stress. Now we have only one shear stress, okay? So we can say that D pure shear is equal to 1/2. And you recognize from solid mechanics that tau yx is equal to tau xy. So this is equal to tau, for example, xy, and we have dx, dy, dz, dx, dy, dz. So that's going to be a common term, dv. And from the first term, we have du, dy. And from the second, we have dv, dx. So that's an expression for the internal stored energy because one single shear stress, in this case, tau xy. Now, anybody recognize what this is? Mr. Gomez, do you recognize what this term is, Mr. Gomez? Mr. Gomez? This is equal to what? Do you remember from your solid mechanics course? No?
Strain.
Exactly, strain. Shear strain. This is shear strain. And this is what you measured, okay, a couple of weeks ago here in the lab. So this is tau gamma xy. And corresponds to this one. So we can say that this is equal to 1/2 tau xy gamma xy dv. Okay. So if you have the other terms, the other shear, the other normal stresses, you can imagine that you are going to have. Okay, so you are going to add all the possibilities. So you are going to have 3 terms for the normal stresses and 3 terms for the shear stresses. And in general, we have to combine all of these six terms. Don't worry, in this class, since it is an introductory class in the area of ship structure, we are going to include only 2 terms, okay? Okay, that's, so don't worry. Now, another thing which is very interesting is that we can take this, okay, we can take this is the volume of the element, and we can put it on the other side. And we can define, for example, a U0. That's going to be the stored energy per unit. So From the previous case, let me go back here. You see that I have this. What I do is I take this differential volume and put it on the left-hand side. And I have 1/2 sigma x epsilon x. Now, this, so I can take this volume and put it on the left-hand side. And I have only 1/2 tau and gamma. Okay, so I'm just going to write, for this case, it's going to be 1/2 tau xy times gamma xy. Okay, so you can imagine that we can have these terms for each one of the types or one of the components of the stress tensor. So we're going to have 6 of these terms. But this is energy per unit volume, okay? And it's quite common to evaluate that and then simply integrate in a deformed body. So that's a very useful parameter, right? Internal stored energy per unit volume. Okay, so it's quite useful. Okay, now let's go on. Now, in the general case, okay, we can have 3 normal stresses and 3 shear stresses. So if we consider the 6 terms, this is what we are going to obtain. Okay, so we're going to obtain the 3 terms for the normal stresses. Okay, so we're going to have the 3 terms for the normal and the 3 terms for the shear. So that's a general case. This is strain stored energy per unit volume. Okay, so if you have this case, okay, I can give you this, and you can say that U is equal to the integral over the whole volume of the body of U0, and that depends on X, Y, and Z times dV. Okay, that's why it is so useful, this amount, U sub 0. Okay, so you estimate that, for example, and then you integrate over the whole volume, and you got finally the total internal stored energy. Okay, now what's next? Since we said that we're going to be working in the elastic range, we can assume, that's what we said, we can assume that the Hooke's law is applicable in our case. Now, the problem is that in general, okay, we have said Hooke's law is sigma x is equal to E times epsilon x. Yes, but that's what for the uniaxial case. Okay, this case is a little bit more complex. Okay, so I'm going to state the general expression, but don't worry, at the end, I'm going to restrict, okay, for the cases that we're going to consider. And those are very simple cases in which we're going to have only a few of these terms, okay? So this is Hooke's law in general for an isotropic material, right? So on the left-hand side, okay, that's a good idea that you try to remember this. It helps a lot. Okay, we have here the strains. All of these are constants. And here we have the stresses. Okay, so we have 3 normal stresses, and they are connected to the 3 normal strains through these constants. We have 0 here, so shear stresses do not cause any elongation of the element. Similarly, these normal stresses, this is 0, do not produce any shear deformation, right? So only shear stresses through this constant produce shear strain. Okay, so that's that. So what we can do now is simply take this term here and replace it here, the second in here, etc. Right? So if we replace this in here, let's do it. Well, not in detail, but let's do some here. Instead of epsilon x, I'm going to use sigma x over E, okay? The other is minus nu pi over E, and the last one is minus nu sigma z over E, okay? So we have to do that for each one of these terms, epsilon y, epsilon z, etc. And then we can collect. Now, you can imagine that in here, you're going to have also a minus sigma x divided by E. So you're going to have sigma x, sigma z, and here you have sigma x, sigma z. So these two will be combined in the next expression here. Okay, so you have the first, when you multiply this sigma x times itself. So you have a sigma x squared. See, this one here times that will give you this. But also, as I said before, you have this times that, right, with negative sign. But you're going to have something similar from this term. So you combine this and you have one half plus 1/2, and this is why you have something like this. This term are multiplied by nu, change sign, and there is the 1/2 does not appear here. Okay, and here you have the corresponding part for the shear stresses. Okay, E, and G. Anybody, what's the relationship between G and E? Mr. Pesantes, what's the relationship between G and E, please? G and E. Do you remember the relationship between G and E?
2 multiplied by 1.
Ah, Mr. Pesantes, please be patient.
Yeah. E is equal to, no, G is equal to E over 2 times 1 plus radiation portion.
No.
Okay.
Okay. What's the typical value of E for the steel? Ms. Jurado, what's the typical value for the steel? Typical for the steel?
Yes, doctor.
Do you remember that?
No, I don't remember.
No, please, everybody, you should have this in your memory, okay? Mr. Vanegas, do you remember the typical value of E? Mr. Vanegas, Dylan Vanegas, do you remember the typical value of E? Vanegas, do you have any problem with the connection? If so, please send me through the chat or through the email, send me a message, okay? Because I don't get any answer from you. Daniela, please. Mr. Medina, do you remember the typical value of the Young modulus? Mr. Medina, do you remember the typical value of E? Come on.
Doctor, is equal to 2.
Now, just a second, please. I want everybody to participate, okay? So please. Mr. Medina, no. Mr. Romero Jandri, are you there? Remember the value of E, typical value of E. Romero Jandri, come on. Romero, please. Daniela, please act. Let me go back here. Ms. Arichua, remember typical value of E.
Good morning, doctor. It's
Hello.
equal to 2.07 per 10 to the 11.
Okay, units.
Newtons over meter square.
Yeah, it's 2.07 e to the 11 newtons per meter square. Yes, and the value of nu, typical value of nu.
Is 1.
What's the typical value of nu? Of
1.
No. Ms. Valdez, do you remember typical value of nu?
0.3.
Yes, 0.3. Yes. Okay, please, these values you have to remember. I'm not going to give it to you in an evaluation. So please put it in your memory, okay? Mr. Carranza, do you remember the value of the sigma of the elastic limit for the steel, normal steel, standard steel? Do you remember?
207.
No, 35. The magic
35.
value. Newtons per millimeter square. Remember, this is equal to megapascals, okay? Sometimes I get confused with this, okay? But yeah, Newtons per millimeter square corresponds to megapascal, okay? So you take megapascals, so that's 10 to the 6 pascals. Pascal is Newton per square meter. You divide it by 1 meter divided by 10 to the 3rd squared, and you get Newtons per millimeter squared. So that corresponds. Okay, now, what happens in our cases? Okay, in our cases, for the analysis of beams, okay, we consider that we have only 2 elements of these strains. And these are the normal strains and the shear strain. That's all, right? So we are not going to have 6 terms as you can see here, okay? Only we're going to have sigma x and tau xy. So in the first part here, you're not going to have this or that, only this one here. What's happening in the second? In the second, you don't have sigma y, you don't have sigma z. So the 3 terms cancel out. We're not going to have any from this thing. And from the last part, we're going to have this and that equal to 0. So we're going to left only with this term. So we're going to have this for the shear and this for the normal stress. And this is what I'm going to present here. So this is the general case. This is internal strain energy or strain energy, linear strain energy, elastic strain energy per unit volume. You multiply times the volume and you got the final total strain energy, okay? In this case, okay, since instead of U, we're going to replace the previous expression, but we consider only 2 cases, sigma x and tau xy, and this is what I'm showing you here, okay? Now, in our case, okay, we could have bars or beams, okay? So in the case of a bar, okay, you have something like this. You have a force like this. And in that case, you can say that this is this. Okay, so this, we're going to assume that it's uniform, otherwise we can get in trouble. And this uniform stress, which is sigma x, will be replaced by P, that's the internal force, this is P, okay, divided by the area. So in this case, sigma x is going to be equal to P of x divided by A of x. So we can take this expression and put it here in a minute. That's for the case when you have in aligned forces, I mean, in the x direction. So this is what we call a bar, okay? Not a beam, a bar, or a truss. Let me write it here. Okay, this is for the case of bar or a truss. Now, let's see for the case of beams, okay? In the case of beams, the load is perpendicular to the x-axis. And immediately, the bending will generate the presence of bending moment and shear force, right? So in this case, to evaluate sigma, okay, We remember we have a beam like this one here. The loading is like this one, okay? And in this case, we're going to have this bending moment, okay? This is the x-axis. Now here, you're going to have sigma x. This sigma x is the one that we're going to replace here, okay? Mr. Kimi, Andres Kimi, would you please remind me, how do you evaluate sigma x in this case? Andres Kimi, how do you evaluate sigma to replace here? In this case, Andres Kimi. Andres Kimi, please. Andres Kimi, can you hear me? Andres Kimi. Andres Kimi, please. Don't make me waste time. Daniela, please proceed. Mr. Fuertes, I'm in the last page. Mr. Fuertes, do you remember how do you evaluate sigma x? Mr. Fuertes, how do you evaluate sigma x? Mr. Fuertes?
Doctor,
You don't remember that?
menos,
Come on, this is the basic expression. You should remember that. Mr. Vasquez, do you remember that?
Yes, doctor. It is minus m sub c times y over I sub c.
It's I sub c, Mr. Vasquez. What is this?
Inertia.
Inertia. What are the units of the inertia?
In that case, it's going to be...
No, in general,
length,
to the what power? To the fourth. Yes. Good, good. And finally, we could have also, in the case of beams, we could have, this is chapter 2, right? We could have a shear force. Okay, this is the same case. This is for beams. Okay, we have lateral load. So this is P of X. We have this, this is the x-axis. And we could have a tau, this is tau xy. Now, let's remind me, how do we evaluate this term here? Okay, we're gonna take this term and put it into here. This here, and this also here. But I want you to remind me how to evaluate tau xy. Mr. Chinchin, please remind me, how do you evaluate tau xy? Mr. Chinchin?
is equal to shear force.
Yes, that's V.
Multiplied by first moment of area.
Yes, Q of Y divided by?
Over inertia multiplied by thickness.
Yes, B of, in general, BS of Y, yes. So that's the way we express it. So we could have, specifically for our case, okay, for this course, we could have only two terms to evaluate the stored or the strain energy. And to replace here, we could have either cases of bars. In this case, we can replace this into here, okay? We can have only also for sigma, because of the bending, we could have this expression replacing here, or we could have this and here if we consider the shear. Okay, we're gonna take a break. It's 8 and 10. We're gonna take a 5-minute break, okay, to recuperate my throat, okay? And we will continue with this analysis.